and thank you everybody for being here, listening this speech the last day. And this work has been done in collaboration between a private company, Advanced Material Simulation, and the University Rey Juan Carlos, both in Spain. In this talk, we want to analyze, basically, we want to analyze if we can determine the fracture toughness of a material from a U-nodes. This is our main idea. U-nodes are interesting element, interesting defect for integrity reason, for validation failure criteria, but also to determine material properties. We are going to apply here this idea. Some words about U-nodes. If we have a crack, we have a singular stress field near the tip of the crack, and we can characterize the failure using a unique magnitude, that is the stress intensity factor. If we have a notch, we have not this singular stress field, but approximately we have Krieger-Pares expression or equivalent, and we can approximate the stress field near the tip of the notch in a similar way. If we fix the radius, we have a magnitude, this is the notch stress intensity factor, to characterize fracture. So have similar situation than crack, but now there is a radius dependence. We have a failure criteria that depends on the material and the radius, but the material dependence is not very strong due to, if we here in this plot, I saw the notch stress intensity factor for ceramic material. There are linear elastic material anti-failure and some polymers with the dimension and without dimension in non-dimensional way. And we can see that if we use this particular formulation, more or less we have a band. We have not a linear, we have not a line, but we have a band, a failure band. This is interesting for apply for fitting for our idea. Now our idea now is to make some experiment with notches to fit the experiment, proposing a failure criteria, using this idea that we have a failure band, and to analyze which is the uncertainty that we are introducing with this modification. Also, it's important that we don't know the failure criteria of the material. So with this methodology, we have a procedure to decide which is the best failure criteria that fit our results. In the University Rey Juan Carlos, they performed at the past, before this research, they performed this test with polyamide in two orientation, in two different orientation, with two velocities, but here is only a pair the static test with four notch radius, and repeating the test with 15 times per condition. So to make a statistic is a good database, because we have 60 tests in zero orientation, and 60 tests with the orientation 90 orientation. The specimen appear the slide are notch specimen with symmetry, and the results we can see that we have few dispersion in orientation 0 and great dispersion with 90 orientation. Now, the idea is to fit with a failure criteria that we are using at this first slide. We are using the maximum local critical distance, maximum stress. We are going to fit the criteria, and we are going to determine in our expression the toughness. And the interesting point is not this procedure. The interesting point is to analyze the uncertainty. The uncertainty that we are introducing with this. We have the uncertainty in the notches, but which is the uncertainty at the toughness. So we are going to apply a Bayesian analysis. We are going to apply this Bayes methodology in which the last line is the interesting point. We are going to calculate the posterior distribution of the toughness using the data that we have, that is the likelihood, is some hypothesis that is the prior distribution. This is the simulation that we have done. We have supposed that the likelihood is Gaussian. It's not very strong hypothesis. It's an experimental error. Also, we are supposing probably this hypothesis is stronger, that in the standard deviation is the same for all the radius. This is the stronger hypothesis. And in this first calculation, we suppose maximum critical distance, maximum stress. We can see that the uncertainty at the first plot, we can see that uncertainty that we are obtaining is not very high. So at the beginning, we can think that this procedure is correct or is not very bad to determine the stress, the toughness, the material toughness from U notches. We have analyzed also the prior, but I'm not going to stop very much here because there is no influence with this prior distribution about the toughness. And this is the results comparing the two orientation. We have looking this plot, we can see that the dispersion is not very high with the notch stress intensity factor. So now with this methodology, we can quantify precisely which is the dispersion with the toughness. In this plot, we can see that we have a great dispersion with the notch stress intensity factor, and this is a methodology to quantify this dispersion at the toughness. The procedure gives us more information due to give us information about the other parameters. In this methodology, we have two parameters. One is the toughness, is a notch radius with radius 0, and the other is maximum stress. That is a notch radius and a notch specimen with radius infinity. So, but this test is not very good for determining due to the radius is not very high, so it's not very good for determining the failure stress. But the important point is the quantification of the uncertainty. So the next step is that we have the hypothesis that we have done is that the failure criteria is local distance maximum stress. Really, we have no reason to do this. We have no reason. Normally, we have no reason to select the failure criteria. We have not objective reason. Probably we have subjective reason. For example, here we have applied this 6 failure criteria: local distance maximum stress, local critical distance mean stress, the strain energy density from Professor Lazzarin and Sambardi. This is the English Professor Filippo Berto has been working. Finite fracture mechanics from Leguillon, although probably this expression is not the last version of this theory. The cohesive sum model with linear softening. Also another criteria that is a phenomenological fitting of the curve that we saw at the beginning. And this is we publish this result. We publish this curve and the other expression in a previous paper, but 20 years ago. And we repeat the simulation with this. The statistical simulation with all these failure criteria, and we can see that now the procedure is not as well as before due to the epistemic uncertainty that we have amplify our uncertainty. If we don't know the failure criteria, we have to take this point into account in our result. And with orientation 0, probably depend of our objective. This measurement is good or not. With orientation 19, the uncertainty is very big. It's very big. What can we do now? Well, we can apply again statistic for model selection. We have this list of 6 models, and we can apply again the Bayes theorem with our data, which is the model that with greater probability. And this is what we done with this criteria. This is Watanabe information criteria that and the minimum value is the best. The minimum value is the best criteria. We can see that in this list, more or less all values are the same. So we cannot say which is the best criteria with orientation 90, but it's the same that we can see in showing this plot. But with orientation 0, we can see that there are 2 groups. One group where this value is in 50, 60, and there are other 2 criteria when this value is near 40. It's very hard to select the minimum. It's very hard to select the minimum because this is not great difference between critical distance, the strain energy density. We can see the same idea if we look the posterior distribution of the toughness. Finishing the presentation. Well, in this presentation, we are proposing a methodology for determining the uncertainty. We have applied to, in this case, to calculate the fractal toughness in polyamide. And it's also interesting due to its methodology for model selection. Probably this is the most interesting point that we have the possibility of select the model. Finally, thank you very much for your attention, and this is our fund. Thank you.